Good morning. Good morning. Please reply me.
Uh,
Yeah, I'm audible for you. Screen is visible. Screen is sharing. Hello.
Screen is visible.
Yeah. Okay. Let's guys. We start the discussion. Whatever we have carried out a discussion on pen and paper. So that I'm again representing here for because there are a problem with their streaming at the time of presentation. So finally I have decided to prepare the ppts and let's start. Now what is a semiconductor diode? The semiconductor diode basically it is having two type of materials, two types are there. One is the intrinsic materials and the second is extrinsic materials. In the intrinsic material, there are a number of holes and the electrons are remain same. Whereas in eccentric materials, again it is has two types, P type materials and the N type. Depending upon their dopant, it can be of N type materials and the P types materials. So if we consider a P type material, in case of a P type materials, there are majorities are the electrons, majorities are the holes and the minorities are the electrons. So here these dotted lines are represented as the holes and the minus signs are represented as a negative acceptor ions. And here are some uh, minority carriers which are electrons represented by dots are there. Whereas for the N type of a semiconductor, the majority carriers are the electrons, which are represented by this small dot, and the minority carriers are the holes, which are represented as a small circle, but these are small in quantity. But when also it will have once the in the N type of a semiconductor crystal, there will be have the positive atoms as well as positive ions as well positive ions which are called as a donors. Similarly, for the P type of a semiconductor, it is have negative ions since it is accepting because if we consider the dopant for this is a trivalent impurities, then one of the electrons will need to be accept, and so it's there will be have acceptor ions are there. Whereas the N type it's have a pentavalent impurities. For the silicon material or germanium material, there will be a four protons will be combined with the electrons, and one of the electrons remains free. So it's a one electrons which is a behave as a free electrons, which is like a as a share donor atoms are there. So finally, we can conclude that the p-type materials is having a majority carriers as a holes, and the n-type of majority carriers as a holes, and the electrons are a minority carriers. Whereas for the n-type of materials, majority carriers are the electrons and the minority carriers are the holes. So what will be if these two structures, if these two if these two materials, P and N type materials, are joined by the process of a fabrication, then the PN junction is formed. Once the PN junction is formed, what will happen? In the PN junction, the here in the PN junction, here these free electrons try to move to the try to cross the junction, and these free electrons will be combined with the holes. Once these electrons will be combined with the holes, then they will be disappear. Once they disappear, they create the ions near the junctions are there. So what will be exactly the free electrons? These free electrons will be combined with the holes, and they will be once they combine, they will be disappear, and this process is called as a recombination. So this electron is donated to the holes. Electrons is behave as a donor and the holes is behave as an acceptor. So this hole is accepting the electrons. So it's a acceptor, and whereas electrons is combined with the holes, which will be a emit, which will be a donate. So here it will be a donor atoms, donor ions are there will be. So or it can say that here, near the junction, positive ions are developed due to the one free electron is combined with one hole. This is one process. At the same time, this hole is accepting the electrons. So it's a one ion is produced, which is an acceptor, which is represented as a minus sign with circle. So it's a negative carriers are there. Similarly, these electrons, free electrons, will be combined with the holes, these holes. Once these will be combined, then there will be a recombination will be takes place and they will be disappear. After the disappear, near to the junction, this free electron is combined with the holes. So they are donating this one. So it's a positive ions will be donated near the junctions, whereas holes is accepting the electrons from so accepting electrons from the n side of materials. So they will be again it will acceptors. So it's a negative ions will be formed. So like in this way, the number of recombination will takes place, and here the positive ions and the negative ions are to be formed near the junctions, and so this positive ions and near the negative ions are formed junction. This will be formed as a deflection width, or it will be represented as a deflection layer. Generally, this deflection layer is around 10 raised to minus 6 meter is there. So as here accumulation of a negative ions and the positive ions from a p side and the n side respectively. So here the one barrier is generated, which this barrier, this is called as a deflection layer, maybe a barrier layer, or this barrier will be a can generate a voltage, or it's called as a barrier voltage with a sign as a here. This is a negative, so it's a negative sign, and this as a positive. So here battery can be a minus sign at for a p side and positive for the n side will be there. So as here the recombination is takes place, the holes are electrons are combined with the holes. Yes. So therefore here you have there will be a recombinant valence band diagram, and there the whole diffusion, holes and diffusion, holes and electron diffusion concentration increase. Now, what is a PN junction diode? PN junction diode can be used as a forward bias or can be used as a reverse bias. What is mean by the forward bias? If we consider that here, if we does not apply any external voltage, then it will be have the no bias. In this no bias situation, there will be a by process of a manufacturing process, p type materials, p type
Excuse me, sir.
materials. Yeah.
Sir,
Hello.
please can you go? Sir, please can you go little bit?
Slow. Little bit. Hello. 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 Please share it.
Sir, please can you go little bit slow? You're too fast.
I'm so fast. Okay. Okay.
Yes, sir.
So I'm taking just reviews, so that's why I'm taking. Okay, we will go move slowly. Okay. So we will discuss that now. We want to study. Let's P type of materials and the N type materials are joined by a process of fabrication process. Then near to the junction, positive ions and the negative ions are to be formed. So for this connection, if we does not apply the external voltage, then this diffusion layer will be formed. by a process of a diffusion or a recombination. So if we apply here external battery to this p side or n side material, the battery can be connected such that positive here and the negative here, maybe a negative here and the positive here. So according to that, if it is connected as positive terminal of a battery to the P side and the negative terminal of a battery to the N side, then that is called as a PN, that is called as a forward bias conditioning. If we consider that the forward bias conditioning, positive terminal of a battery is connected here. Yes, so we will take it this one diagram. Okay, here positive. Positive terminal of a battery is connected to the N type and the negative terminal of a battery is connected to the P type. So as it is connected, so this terminal will be emits its ions. Yes, this terminal positive ions and the negative ions. So as what is here? Here we will have the electrons, majorities are the electrons, minorities are the holes, and for the p side you will have the majorities are the holes and the minorities are the electrons. So as this battery emits the ions, and and the same thing that across the deflection layer, here it is you have the negative ions, negative charge carriers, and for the n side we have the positive charge carriers. So if we concentrate for this external voltage V, it's have a positive as well as a negative. So this negative terminal, it's emits negative ions. So these negative ions will be entering in this direction. It's at the metallic contact and here. Now what is here? Here we will have the majority electrons as well as the minority holes. So these negative ions will be combined with here a deflection layer ions. Now what is the deflection layer ions are here? Here are a positive ions. And this emits the electrons, the negative ions emitted from the negative terminal of a battery is combined with this one at the near to the junction. So as it is a combining near to the junction, what will have this deflection width, which was before applying external volt, it will make it reduce. It's a combined, they will be disappear. Once this disappear, this will be a width will be a goes reduce. Similarly, what will happen for the p side? From a p side, as a positive terminal of a battery is connected to the n type, so the positive terminal will be emits positive ions. But at the near to the junction on a p side, here is a negative ions are there. So these positive ions and the negative ions, positive ions and the negative ions are will be combined with there, and so this deflection width will be goes now reduce. So as the deflection width goes now reduce, yes, so there will be have the less resistance, or they will be have here less potential will be developed across the PN junction. PN junction will be there. So for PN junction diode, when it is configured as a forward bias, if we consider material is made up of with a germanium material or maybe a silicon material, for a germanium material, this forward voltage across the junction, it will be a zero point 0.3 volt, and for silicon material, it will be 0.7. So when the current will start the flowing, when the potential at this point, potential applied from external source voltage V is a greater than potential available at this point. Now what is the voltage available at this point? It may be a 0.3 or it may be a 0.7 for a germanium material and silicon material respectively. If this applied voltage is greater than this voltage, this barrier will be break. And once this barrier will be break, there is no opposition, and the electrons will be start so moving like in this way. Right? It's actually electron direction, and the current direction will be like in this way. So it's a positive to the p side material, deflection layer, n side material, and the negative terminal. This is a direction. and this actually is, these dotted lines are indicates the actual flow of electrons. Remember that, guys, the electrons will be flows from a negative terminal to the positive terminal will be there. So what will have? This is a forward bias conditioning. So means once the barrier potential across the PN junction is break under condition that applied voltage is greater than barrier potential. So then the current will be flows, and so up to the barrier potential, there is a small recombination will takes place, and so small amount of a current will be flows. Once the applied voltage is greater than barrier potential, this barrier will be break and the current immediately flows, which will be a. So we will slightly summarize this. Yes. So the electrons from a negative bias terminal continue to arrive into the N region, while the free electrons in N region move towards the PN junction. The electrons travel through N region as a free electrons, that is, the current in N region is by a free electrons. These electrons on a reaching PN junction combine with holes and become valence electrons. Since the hole is in the covalent bond, and therefore when a free electrons combine with hole, it becomes a valence electrons. The electrons traveling through P region as a valence electrons, and the current in a P region is therefore by the holes. These electrons, these valence electrons, on reaching to the left end of a crystal flow in the positive terminal of the battery. So thus, we can say that the current in a p-type region is due to the movement of electrons, whereas in a p-type region it is by mean of holes. So what about the reverse bias? Under the reverse bias, what will happen, guys? Now the battery polarities are reversed. So for a reverse bias, negative terminal of a battery is connected to the P side, and the positive terminal of a battery is connected to the N side. So as here, if this battery is not connected by the process of a diffusion, by process of a manufacturing process, P-type materials and N-type materials are the joined, and once they join, there will a recombination process will be takes place, and here deflection layer is formed with positive ions in the N regions and the negative ions in the P regions. We have discussed this one. Now, if we apply a for negative terminal to the here to the P side and positive terminal to the N side, so the positive terminal will emit positive ions and the negative terminal of a battery will be emits negative ions. So these negative ions will be combined with the positive ions or positive carriers available at near to the deflection layer. Similarly, these positive ions from the positive terminal of a battery, it will be combined with negative terminal of it will be combined with negative carriers of the junction, negative carriers of a junction in the P region. So what will have? Sure it will be combined? No, here it is a positive ions, here it is a negative ions. Now here it is a negative ions will be never combined, and here positive ions will be never combined, because it will have the positive ions available at the junction and the positive ions coming from the battery. It will be accumulated. They will be a does not take place recombination. Similarly, here negative ions and the negative ions or negative carriers from the negative terminal of a battery is again also coming up to the PN junction, and here the as the both are negative ions, negative carriers are there, so there is a two combination will takes place, so that therefore here it is a more accumulation of a positive ion, so negative ions near to the junction from in the P side, and the more accumulation of positive ions will near to the junction in the N region. So therefore, this deflection width, which was small as compared, which was small in case of a no applied voltage, will be a more wider in case of a reverse applied voltage. So as here barrier is a more, so it is a definitely here barrier potential will be more. So when this barrier potential will break, when this reverse voltage is a reverse voltage is a greater than this barrier potential, then it will break. So as here electrons here as a positive ions are accumulated near the junction in a p region. Here are negative ions are accumulated near to the junction in a p region. Yes. So therefore, what does it is reflects that deflection width goes on increasing it. So the barrier is bigger. So therefore, the movement of electrons from N region is not going to the P region. So therefore, will be a no recombination. Similarly, majority holes from the P side is not combined with N side since barrier is more. So there is a recombination, there is no recombination of a majority carriers with the majority carriers of a P sides and the N sides. So therefore there will be no movement of electrons and holes due to the majority carriers. But here the small amount of small amount of a collection will be there. So its barrier is a more, no current is a flow. So what will be a current flow for this one? So this will be for reverse bias. No movement of electrons across the crossing the junction. So no current will be a flows through this configuration. And this configuration is called as a reverse bias configuration. So guys, finally we can summarize that for a forward bias, there will be a flow of majority carriers. Yes, so there will be a majority carriers from the P side as a holes and from the N side as the electrons are there. Okay, so and for the reverse bias there is no movement of majority carriers from a p side as well as p side to the n side and electrons from a n side to the p side. Therefore there is no movement, therefore there is no flow of a current. So finally we can say during the forward bias condition, current is a flow, and during the reverse bias condition, current is never flow. So directly, we can say that the PN junction diode can be simply behave as a on and off switch. So here we have that here we have that during this PN junction diode can be used as a switch, open switch and the closed switch. When it is a closed switch, when the diode is a forward bias, it will behave as a closed switch, and if it is a if it is a reverse bias, it is a behave as a open switch will be there. So finally, we can say that for the PN junction diode, the current will be a flows during if the diode is a forward bias and the current is never flow in the reverse bias, but the small amount of a current is a flows in the reverse bias, which is due to the minority carrier combination, and this current is generally in a picoampere will be there. So during the forward bias condition, current flows. During the reverse bias condition, current never flows. So we can say that the diode is a unidirectional. So it can be used as a unidirectional device. So we summarize the reverse applied voltage. When PN junction is a reverse bias, the barrier is increased and the width of a deflection is increased. The junction offer high resistance called as a reverse resistance to flow of a currents. owing to the establishment of a high resistance path, a very small amount of a current called as a reverse current or leakage current flows through the circuit. So guys, remember that here it is a small amount of a current is a flows due to the minority carriers of the minority carrier combination will be there. Whereas for the forward bias, there is a majority carrier combinations are responsible. So the reverse or a leakage current is not affected by the barrier and depends on the temperature, materials and the construction of the junction. So thus we can say that the PN junction allows a flow of a large current only with a forward bias and only a small reverse current or a leakage current when a reverse bias. So what is happening to the zero bias? Already we have discussed that. Means no bias. In the no bias, by the process of manufacturing, the P side material and the N side materials are joined. Yes, these free electrons will be combined with the combined with the holes as there is a combination, the recombination takes place and this recombination will be a disappear there these ions, and so we will have here a p side we have the positive ions will be developed and the n side negative ions will be developed since this electrons is emitting or it will combine with the holes, so it's behave as a donor and this is accepting the electrons from the p side, so it's a acceptor and it's a creator negative ions. So this is a like in this way one electrons is a combined with the holes, number of electrons is a combined with holes and the junction layer will be formed. Okay, so here it's a Fermi level for this one. Remember that Fermi level for the zero bias applied is at the center of the energy bands. So it's a seen that as the electrons are moved from a majority electrons are moved from a p side to the n side. So therefore, the concentration level of a here in a p side goes on a decreasing rate. Whereas similarly, the whole sides are combined with the electrons. So similarly, concentration of a holes is also decreasing it from a yes p side to the n side, and here concentration of electrons is changed from a n side to the p side. Finally, we can say from a p side to the n side, the concentration of a holes is goes on a decreasing rate, whereas the concentration of electrons is goes on increasing it from a p side to the n side will. Yes, and so as here the concentration is changing it, the deflection width will be formed, and this deflection width will be developed. It's a barrier which is called as a barrier potential, represented as a built-in potential barrier by a subscript which by labeling as a VB subscript VI. So this is a difference, which is a barrier potential. So what will we have? Now discussion on this one. Now what is it that we want to find out what will be a barrier potential? In the intrinsic Fermi level is equidistance from the conduction edge to the junction as shown in the figure. Okay. The potential barrier is the difference between the intrinsic Fermi level of a P and N, and which is given as the VBI is equal to VBI is equal to phi Fn plus phi Fp. The electron concentration in N region conduction band. So guys, all these expressions by considering of semiconductor physics. So according to that, here electron concentration in N region is given as N0 is equal to Nc e raised to minus E subscript C minus EF divided by K dash T. Now, what is the T? T is in temperature, T is a Boltzmann constant, and here A subscript F, it's a Fermi energy level, and A say it's a conduction band Fermi energy level, and N say is a concentration, carrier concentration. So, where are the Fermi levels under respectively? So, the potential phi Fn in the end region, this potential in the end region as well as the p region we need to find. So this will be your E phi Fn is equal to this Fermi level, energy Fermi level minus E. So therefore, taking the natural logarithmic of both this side, okay. So taking natural logarithm to the both the side of equation 2, we have that phi fn is equal to minus k dash t divided by e log of e nd divided by ni. Similarly, for the p region, it can be given uh, as here the electrons are there, in the majorities are the electrons, and for p region majorities are the holes, so this signs will be a positive, and for the p side there is a acceptor, and for the n side there is a donor. It will be like this. So we have thus the built-in barrier potential for a step function is given as this one. So k dash t divided by e log to the base e and a divided by e. So what is, we have to club these two. If we club these two, we have the common part of this one. So here it is a logarithmic subtraction, logarithmic subtraction. So logarithmic subtraction gives you the logarithmic division. So finally, you have this expression will be there. So where on this one, this is called as a K times T divided by E, which is represented as thermal voltage, and the thermal voltage is depends on the temperature, which is given as a T divided by 11600. So finally, you will have the contact barrier potential near to the junction is given as VBI is equal to VBI is equal to Vt log to the E log to the base E Na divided Na into Nd divided by Ni square. Yes, here it is acceptor, here it is a donor. Now we want to solve one numerical based on the previous expression. The resistivity of a P region and the N region of a germanium diodes are 6 ohm centimeter and 4 ohm centimeter respectively. P region and the N region. Calculate the contact potential barrier voltage of that Q is equal to 1.6 into 10 raised to minus 19 coulomb, guys. It's a 10 raised to minus 19. This and Ni intrinsic level will be a 2.5 into 10 raised to 13, guys. It's a 10 raised to 13 per centimeter square. Mobility of a P is a 1800,000 centimeter per voltage, and the mobility of electrons is a 3800 is there, guys. 3800, 10 is happened more, guys. Please kindly rectify this one. Okay. So and the Vt is equal to 0.023 volt at a 300 Kelvin temperature. So or 26 millivolt will be there. Now we want to calculate the contact potential barrier. Now, what will the contact potential barrier? We have this expression. Contact potential barrier is given as a Vt log to the base E Na divided by Nd divided by Ni. Yes. Now we want to find this value by using this expression. What is a Vt? Vt they have given. We need to find the acceptor concentration as well as the donor concentration and an intrinsic level will be there. Now, firstly, we will find what is the donor and the acceptors are their values. So, firstly, we want to find the density of electrons, yes, and the density of protons. So, sorry, density of holes. So, density of holes is represented as a n subscript A, and the density of electrons is represented as a n subscript T. This density is given as, yes, sigma I divided by electrons into the mobility of electrons. So this sigma is what is a conductivity, and the conductivity is related with the resistivity is a conductivity is inversely proportional to the resistivity. So we have it 1 upon resistivity of a n region. So this resistivity is given, which is a resistivity is given as a for, yes, P side we will have the holes, at the N side we will have the electrons, which is a 4 ohm per centimeter. So we will have this resistivity is a 4. So 1 upon 4 centimeter divided by its this E charge is given that 1.6 into 10 raised to minus 19, and mobility of electrons is given as, guys, 3800. 10 is a more happened, guys, so please neglect this one. So you will have, if you compute this, you will have it 4.1 into 10 raised to 14 per centimeter cube. Similarly, we can find the density of a protons as well, or density of a holes. So, and the density of a holes, it is given as that the 1 upon resistivity of a holes. What is the resistivity of a holes? It's a 6 ohm per centimeter. Yes, it's a 6 ohm. Sorry, it's a guys, it's 6. Okay. So one more rectification, guys, here it's a 16. Okay, so if we consider that here, this value we will have a 5.78 is there. It's a 16. Now plugging all these values, we have found out a density of electrons as well as the density of holes. So if you plug all these values in the contact carrier potential expression, which is labeled as VPI is equal to VT logarithmic to the log to the base E, density of holes into the density of electrons divided by intrinsic constants, which is Ni, is given as this one expression. Now what is the next volt ampere characteristic of a PN junction? So since that diode can be used as a forward bias, can be used as a reverse bias. For a forward bias, so P type of a battery is connected to the N side, and the negative terminal of a battery is connected to the P side. It's called as a forward bias. And during the forward bias, majority carriers of electrons from the P region and majority electrons from the P region will be combined with majority carriers of holes in n region. Yes. So therefore, in the when diode is a forward bias, majority current will be flows. The current will be flows due to the majority carriers like holes in the p region and the electrons in the n region. So they will be for a forward bias. There will be a less barrier potential. So junction potential is less barrier, less opposition, less forward voltage will be there. And once this forward voltage is a break, the current will be a starts flow. Before a breaking, small amount of a current is flowing, which is generally a micro ampere. And once this barrier potential is a break, yes, once this barrier potential is a break, then immediately current will be raised. So this is the one of the characteristics for the germanium material, and this is the one of the characteristics for the silicon material. So for a silicon material, its barrier potential is a zero point 0.7, whereas for the germanium material, its a barrier potential is a zero point 0.3. So barrier potential can be also known as knee voltage. What is the knee voltage? That parameters we will discuss later. So from this graph, it is saying that when diode is a forward bias, yes, the current will be slowly increasing it up to its new voltage. Yes, once the applied voltage is a greater than new voltage barrier potential, then this barrier will break across the junction and the current will be a flows. So this is a forward bias characteristic. What about the reverse bias? In the reverse bias, when the negative terminal of a battery is connected to the negative terminal of a battery is connected to the P side and the positive terminal of a battery is connected to the N side, then the by process of then there across the junction deflection width become more wider, but deflection width become more. So as the deflection width is more barrier is there, more voltage will be appear at the junction, more voltage which is represented as a reverse voltage, barrier is a more voltage. So reverse in the reverse bias, barrier potential is more, and when this barrier potential is break, when the applied voltage is around when the applied potential is around when the applied potential is more than barrier potential of under the reverse bias, then current will be flows. But before the before the breaking, there will be a combination of electrons and holes which are minority carriers. So due to the minority carriers, the electrons will be a small amount of electrons will be flows, small amount of leakage current is flows. So this can be a small amount of current which can be labeled as leakage current, can be labeled as reverse saturation current, and so on. So finally guys, actual diode characteristic is like this way if we combine diode forward bias as well as the reverse bias. So therefore, here we have this is a forward bias region where the potential across a diode is greater than 0 and then current is also greater than 0. Whereas for the reverse bias, this potential is less than 0 and the current flowing through is also less than 0. Small amount of current is flowing through this one. Guys, it's a reverse bias region. Shaha, please move yours. Shaha, move your side. And there is a no bias point where it is right here, where applied potential diode voltage is 0 and the diode current is 0. So the important term
अरे
associated
काय
with this.
कळत नाही ग बाई.
अरे आदेश असं चालणार नाही. थोडं लक्ष त्याच्यात घाल. हे बघ,
बरं घालतो.
तू ओव्हर कॉन्फिडन्स मध्ये जाऊ नको. पहिल्या वर्षी चुकलं म्हणून तू ऑल क्लिअर होत असेल. एवढं चेष्टा नाही इंजिनिअरिंग.
मला पण माहित आहे ग मम्मी. ठीक आहे चल
Hello.
उठ तू, लक्ष दे
घालतो. हा
त्याच्यात.
Shaha, move your side. Okay. Next, guys. After finishing these lectures, you have to give your attendance on our WhatsApp group, and I conclude that here. The first lecture is sorry, today's lecture is over. So next time we will start with again from the VI characteristic of a diode.